I am Second Lieutenant J.P. Mason. I'm with the 804 Squadron. I also am a private pilot. I'm currently working on getting my other ratings as a student for as a career in aviation. And I'm here to teach you today about aerodynamics, which is a very important thing in aviation. It's actually one of my favorite topics because it's about how aircraft move through the air. Aero is Greek for air. Dynamics is how solid objects move through a fluid object. The fluid object being, in this case, the air itself. So I was able to locate a couple of videos that I think get the point across very well. So I'm going to play them for you. I'll stop here and there if you guys have any questions or if I need to chime in and give you some other information. And if you have any questions, please feel free to raise your hand and interrupt, and I'll be happy to answer, okay? Okay?
Yes, sir. Yes, sir.
All right. Can everyone hear?
Yes, sir. Yes, sir.
Tutorial 4, Aerodynamics of Flight. This training tutorial will discuss aerodynamics of flight. In order for a pilot to safely execute maneuvers in flight, it is important to understand the aerodynamic forces acting on an aircraft in flight. The four forces acting on an aircraft in straight and level, unaccelerated flight are thrust, drag, lift, and weight. Thrust is the forward force produced by the power plant, propeller, or rotor, and is opposed by drag. Drag is the rearward, retarding force caused by air that has been disrupted by the wings, rotor, fuselage, and other protruding objects, and opposes thrust. Weight is the combined load of the aircraft itself, the crew, the fuel, and the cargo or baggage. Weight pulls the aircraft downward because of the force of gravity and is opposed by lift. Lift opposes the downward force of weight. Lift is produced by air flowing over the airfoil and acts perpendicular to the flight path through the center of lift. In straight, level, and unaccelerated flight, the sum of the forces acting on the aircraft is zero. This is, for the most part, true during climb and descending flight, but things are a bit more complicated. Anytime the flight path of the aircraft is not horizontal, lift, weight, thrust, and drag vectors must each be broken down into two components. For example, during a glide, part of the weight of the aircraft points forward and therefore acts as thrust, or as the picture shows, during a climb, the weight can oppose lift and also thrust. A pilot may hold an aircraft in straight and level flight at many different airspeeds. The pilot needs to coordinate the angle of attack with the speed of the aircraft. For example, if the plane is flying at a high rate of speed, the angle of attack can be relatively low. However, if the rate of speed is low, then the pilot must have a higher angle of attack. This is caused by the amount of lift produced by the wings of the aircraft. The higher the angle of attack, the more lift is provided from the wing. If a pilot can maintain a high angle of attack and a coordinated thrust level, the aircraft can fly straight and level at low speeds. Level flight at even slightly negative angle of attack is possible at very high speed. Certain aircraft have the ability to change their direction of thrust rather than change their angle of attack, such as the Harrier Jump Jet on the left and the Osprey on the right. These aircraft can point their thrust straight up without having to point their nose in that direction. The Harrier Jet uses vents to accomplish this, and the Osprey can rotate its propellers to point up. This allows each aircraft to hover over the ground or fly straight and level very slowly. Drag is the force that resists movement of an aircraft through the air. There are two basic types, parasitic drag and induced drag. The first is called parasite. because it in no way functions to aid flight, while the second, induced drag, is a result of an airfoil developing lift. Parasite drag is any drag that is not caused directly from the aircraft producing lift. It is broken down into three categories: form drag, interference drag, and skin friction. Form drag is a drag that is caused by things like the cowling, antennas, and the aerodynamic shape of other components. How quickly airflow rejoins itself is determined by the shape of the object it's flowing around. As the picture on the left shows, the best way to reduce form drag is to streamline as many of the aircraft components as possible. Interference drag comes from the intersection of airstreams that creates eddy currents, turbulence, or restricts smooth airflow. For example, the picture on the right shows the intersection of the wing and the fuselage at the wing root. This area has significant interference drag. Air flowing around the fuselage collides with air flowing over the wing, merging into a current of air different from the two original currents. Skin friction drag comes from the surface of the aircraft not being completely smooth. Even though a surface may look smooth, it has a rough, ragged surface when viewed under a microscope. This non-smooth surface causes an interruption in airflow and more drag.
Now, briefly, have you guys gone over aviation weather at all?
Yes, sir.
Yes, sir.
Okay. The skin friction, did they talk about frost?
Yes, sir.
Yes, sir.
Frost is also a form of skin friction. So with all the frost on the wings, can cause the air to break up sooner, and therefore cause less lift, and also would cause issues with aerodynamics. And that's why it's always a good idea to make sure your aircraft is clean at all times, especially during bad weather.
Induced drag is the second basic type of drag. When an airfoil produces lift, there is always drag. This drag comes from wingtip vortices. When the aircraft is viewed from the tail, these vortices circulate counterclockwise about the right tip and clockwise about the left tip. Bearing in mind the direction of rotation of these vortices, it can be seen that they induce an upward flow of air beyond the tip and a downwash flow behind the wing's trailing edge. This induced downwash has nothing in common with the downwash that is necessary to produce lift. It is, in fact, the source of induced drag. This downwash over the top of the airfoil at the tip has the same effect as bending the lift vector rearward. Therefore, the lift is slightly aft of perpendicular to the relative wind, creating a rearward lift component. This is induced drag. Drag is the price paid to obtain lift. The lift to drag ratio is the amount of lift generated by a wing or airfoil compared to its drag. This also governs the airfoil's efficiency. Aircraft with higher lift-drag ratios are more efficient than those with lower lift-drag ratios. The lift-drag ratio is determined
That's the green
by
right here.
dividing the lift component by the drag component, or above by dividing the lift equation by the drag equation. L is the lift force in pounds. CL is the lift coefficient. P is density expressed in slugs per cubic feet. V is velocity in feet per second. Q is dynamic pressure per square feet. And S is the wing area in square feet.
Remember, this is on
On the
test.
graph to the left, the lift
That's a
curve,
joke.
red, reaches its maximum for this particular wing section at 20 degrees angle of attack, and then rapidly decreases. 15 degrees angle of attack is therefore the stalling angle. The drag curve, yellow, increases very rapidly from 14 degrees angle of attack and completely overcomes the lift curve at 21 degrees angle of attack. The lift-drag ratio, green, reaches its maximum at 6 degrees angle of attack, meaning that at this angle, the most lift is obtained for the least amount of drag. Any angle of attack the aircraft operates at, other than the lift-drag max point, will cause more drag. Therefore, for the least amount of drag to lift, the aircraft must fly with that angle of attack. Gravity is the pulling force that tends to draw all bodies to the center of the Earth. The center of gravity may be considered as a point at which all the weight of the aircraft is concentrated. If the aircraft were supported at its exact center of gravity, it would balance in any attitude. This weight force acts downward through the airplane's center of gravity. In stabilized level flight, where the lift force is equal to the weight force, the aircraft is in a state of equilibrium and neither gains nor loses altitude. If lift becomes less than weight, the aircraft loses altitude. When lift is greater than weight, the aircraft gains altitude. The pilot is able to control lift. If the control yoke is pushed forward or pulled back, the angle of attack changes and therefore the amount of lift changes as well. For an aircraft to continue to produce lift, the aircraft airfoil must be continually attacking new air. On helicopters, this is accomplished by the rotating blades. In a fixed-wing airplane, this is accomplished by the airflow over the wing. The lift provided from the wing is proportional to the square of the aircraft's velocity. Lift and drag also vary directly with the density of the air. Density is affected by several factors: pressure, temperature, and humidity. At an altitude of 18,000 feet, the density of the air has 1/2 the density of air at sea level. In order to maintain its lift at a higher altitude, an aircraft must fly at a greater true airspeed for any given angle of attack. Warm air is less dense than cool air, and moist air is less dense than dry air. Lift varies directly with the wing area. If the wings have the same proportion and airfoil sections, a wing with an area of 200 square feet lifts twice as much at the same angle of attack as a wing with an area of 100 square feet. For most situations, the pilot controls lift and velocity to maneuver an aircraft. As stated previously, wingtip vortices are caused when the high pressure below the wing attempts to rejoin the low pressure air around the wingtip, causing a downward and outward vortex. The above picture is a more detailed diagram of how this process looks on a wing. The heavier and slower the aircraft, the greater the angle of attack and the stronger the wingtip vortices. Wingtip vortices lead to a potentially hazardous condition called wake turbulence. To avoid wake turbulence, avoid flying through another aircraft's flight path. Rotate prior to the point at which the preceding aircraft rotated when taking off behind another aircraft. Avoid following another aircraft on a similar flight path at an altitude within 1,000 feet, and approach the runway above a preceding aircraft's path when landing behind another aircraft. And finally, touch down after the point at which the other aircraft's wheels contacted the runway. A hovering helicopter generates a downwash from its main rotors similar to the vortices of an airplane. Pilots of small aircraft should avoid a hovering helicopter by at least 3 rotor disc diameters to avoid the effects of this downwash. Wind is also an important consideration when dealing with wake turbulence because it can push around wake turbulence. For example, if there's a 10-knot wind, it will push the wake turbulence in the direction of the wind at a rate of 1,000 feet per minute. If this is a problem, pilots may also wait approximately 3 minutes for the wake to dissipate.
Now, a bit more on the wake turbulence itself. It said the biggest wake turbulence created is when the aircraft is slow and heavy. Now, when is the aircraft at its slowest and heaviest? Cadet?
Cadet Master Sergeant Schreiner when it's landing, sir?
Incorrect. Yes?
Sir, an aircraft is traveling slowest and heaviest on takeoff?
Correct. That's when it's at its slowest and heaviest and therefore the most dangerous. Especially if you're in a small aircraft like a Cessna or anything, any kind of trainer you usually start off in. And you're practicing like here at ABE. when any of the big jets take off, they're the most dangerous, their wake turbulence is the most dangerous when they take off because they're clean, so they don't have any flaps down, they're slow, and they're the heaviest because they have the maximum amount of fuel and passengers and luggage. So if you go behind those in a smaller aircraft or anything like that, and you don't wait enough time for the air to dissipate, especially with the wind, it can cause the aircraft that you're in, especially a small one like that, to easily flip over, crash, veer off, whatever. It's not a good thing. Another thing to consider with wake turbulence is, again, like they said, the wind. Now, if you will have a nice headwind where the wind's blowing down the runway and you're going off into the wind, usually the wind can dissipate, usually the wake turbulence can dissipate at the rate that the instruction told you. Or if you get a crosswind and it blows it off the runway. The worst type of wind you can deal with wake turbulence is a tailwind, meaning the wind is pushing you down when you're coming down. So you already have a wake turbulence created from a jet that either took off or landed, and what's worse is it's supposed to go this way, but if the wind is a tailwind, it's going to push it and keep it right there. So it's going to keep it there for a longer period of time, and therefore you might either have to wait longer, or like the instruction said, land beyond where the aircraft landed. Therefore, that's your best bet to avoid the wake turbulence altogether. You had your hand up?
Cadet Airman First Class Aerodynamics. Sir, I have a question. What about the engine? Would that cause wake turbulence?
Not so much. It's the wingtip vortices are the biggest cause of wake turbulence. I mean, the engines, especially if you're talking like the jet engines of those aircraft, not so much wake turbulence. They create, thrust, and the thrust can be dangerous. But most of the time, you're far enough away from the aircraft that the thrust of the engines don't affect you. I'm sure some of you have probably looked on YouTube. You've seen a video of the jet engine, and you see the car driving down, and gets knocked away. That is less likely to happen if you're away from the jet, because the thrust usually dissipates quicker. It's the wingtip vortices, that generation of slow and fast wind coming together and creating that vortex, is a bigger danger than the thrust of the aircraft. And even like a small propeller engine, I've stood behind small single engine aircraft propeller while it's taxing or increasing its thrust, and kind of close your tire on a bit, but it dissipates rather fast, so it's a bit different. Any other questions? Yeah, another one?
Cadet Airman First Class Aerodynamics. What about for formations, like when fighter jets are in formation? Why are they not losing control?
That is a bit beyond me, because I haven't done formation flying yet. We've tried to get a couple of us to do it with the insurance agents. The insurance company won't let us. Usually, because they're right next to each other, they're right where the wingtip vortices are being created. So they're small enough at that point in time that they're not a hazard. As you can see here, the farther away you are on the video here, the farther away the aircraft is, the bigger the wingtip vortices, and therefore potentially the more dangerous it is, until of course it dissipates. So when you're formation flying, most of the time you've got aircraft flying like this with each other. So they're kind of side by side. So you can see where they're sitting here. The vortices are basically just starting, and it's all the vortices together. So most of the time, that's not an issue. And that's with any of those aircraft, especially if you're talking whether it's propeller or jet engine. Most of the time they're going fast enough and they're close enough to each other that wingtip vortices shouldn't cause an issue for them. Unless of course you're talking like in the movie Top Gun, where Maverick, who here hasn't seen Top Gun? You have not seen Top Gun? Get out of my classroom. You all failed. You're in the Air Force and you haven't seen, well, then again, Top Gun is a Navy movie, but still, it's still about aviation. Watch Top Gun, that's part of your homework.
It's on Netflix.
It's on Netflix, see? No excuse. All right, anyway, using the Top Gun scenario, even if half of you haven't seen it, what happens is the lead fighter pilot in his aircraft is targeting a dummy plane for training. And the his wingman is behind him and like right around here. So he's right in the center of everything. He's in the center of the guy's wake turbulence, his thrust, and all that stuff. The lead pilot can't get a shot on the target. Second guy, Maverick here. Maverick tells Iceman, break off, I've got a shot. He breaks off. The wingtip vortices and the thrust of his engine goes right into the fighter craft's engine intakes, causes an engine burnout, and without spoiling the rest of the movie, something bad happens. The aircraft goes into a spin, and I'll leave it at that. So that would probably be where the bigger risk factor is, as far as wingtip vortices and like propulsion goes, is if they're in a very bad position like that. But most of the time, stunt pilots and teams like that, they're usually within this area of each other. They're mostly wingtip to wingtip, give or take a few feet up or down, left or right. They're not far enough back and behind, right in that sweet spot where it's dangerous. Any other questions? All right, let's continue with the video.
Ground effect is a phenomenon that allows an aircraft to fly slower than normal a few feet from the ground. When an aircraft in flight comes within several feet of the surface, ground or water, a change occurs in the three-dimensional flow pattern around the aircraft because the vertical component of the airflow around the wing is restricted by the surface. This alters the aerodynamics of the wing mainly. The fuselage and tail surfaces are also affected, but ground effect mainly consists of the aerodynamic characteristic changes of the wing. The reduction of the wingtip vortices due to ground effect alters the lift distribution of the wing and reduces the induced angle of attack and induced drag. Therefore, the wing will require a lower angle of attack in ground effect to produce the same lift. The reduction of induced drag due to ground effect means that less power is required to fly at a certain speed. Most of the time, ground effect will produce a higher pressure at the static source, and the incoming airspeed will be lower than normally required.
Now, quickly on that as well, what she didn't really say much, as far as an explanation goes, is it almost acts like a cushion of air that kind of catches the wing when you're coming down, mostly for a landing. And this usually happens about the length of the wingspan of the aircraft. So usually once you're about a wingspan above the ground, usually when you're coming in for landing, that's when ground effect usually kicks in. And that's why you can usually fly and hover over the runway for an extended period of time, because you have the cushion of air. Especially if you have a nice power setting in there, very low setting, and you have the right angle of attack, you can hover it. And that also helps with landings as well, because you've got that cushion of air to help slow you down just enough for you to softly touch on the ground. Now at the same time, ground effect can also cause problems. There'll be another video I'll be showing later on showing kind of a hazard of the difference between ground effect and also a very strong crosswind during ground effect and what it can cause to the aircraft. It's actually a personal experience. It's a video that I recorded, so it'll be a fun little thing I'll show at the end here, and how it'll look in an actual aircraft with ground effect and crosswind. Thankfully, no, wingtip vortices or wake turbulence. That would have been really bad, but close enough. All right, any questions about the ground effect? Okay, we'll continue here, and we'll be just about finished with part 1.
When an aircraft is taking off, the reverse happens from landing. The aircraft taking off will require an increase in angle of attack to maintain the same lift, experience an increase in induced drag and thrust required, experience a decrease in stability and a nose-up change in moment, and experience a reduction in static source pressure and increase in indicated airspeed. This is something to consider on takeoff, because it could mean a pilot attempting to take off will feel like the aircraft can lift off the ground prior to the recommended takeoff speed. As shown above, this could cause the plane to have poor initial climb performance, and also, in extreme cases, prevent the aircraft from becoming airborne entirely. Axes of an aircraft will be covered more in depth in the flight controls chapter.
Now, real quickly here, even though she kind of only slightly touched upon it last second there, but who here knows what causes the aircraft to pitch? What control do you use to make the aircraft pitch up and down? Let's see, whoever I picked on yet. Schwartz.
Okay, for Class Schwartz, I believe that would be the flaps.
Incorrect, Schwartz. Sit down. You, sir.
Cadet Technical Sergeant Swarthy, sir, I believe it is the ailerons.
Also incorrect. Now, let's see, who else here? You in the dress blues in the back, Cadet. Sorry.
That Senior Master Sergeant Casrio, the elevator, sir.
Correct. And what part, bonus question, hold on, keep up there. Bonus question, what control, what do you use that actually creates the elevator to go up and down?
Use the yoke, sir.
Correct. All right, thank you. All right, next question. The rolling of the aircraft. What controls cause the rolling? Both the outside of the aircraft as well as the actual control you manually use. Anyone? Oh, Scheller?
Yeah, Lieutenant Colonel Scheller. The ailerons are what make it actually roll on the outside, and you turn the yoke or the joystick in order to make the ailerons move.
Correct. So, with the Master Sergeant as well as Lieutenant Colonel Hill, the yoke controls two aspects of the aircraft itself. The pitching and the rolling. Pulling up and pushing forward takes the aircraft up or down respectively in the pitch. The left and right of the joystick or yoke makes the aircraft roll left or right using the ailerons. Now the ailerons, I'm sure most of you know, are here on the outer edges of the wings. That's what actually causes the aircraft to roll. The elevator is back here. Now, final question. Yawing. What causes the aircraft to yaw? Who haven't I picked on yet? You.
The airman first thoughts were the rudder.
The rudder, correct. And what causes the, what do you use to control the rudder?
The foot pedals, sir.
Correct. All right, and that is correct. The foot pedals for the rudder are, just like on the car, except you have two, except instead of a brake and a gas, it's right and left rudders, or as well as how to control the rudders. Now, bonus question here is not on here. How do you control the aircraft on the ground? How do you make it turn left and right? You.
So you would use the rudder?
Correct. You use the rudder pedals as well. And there's also toe brakes on most aircraft as well that you can use for differential braking to help you turn as well while you're on the ground. All right, very good. So that covers aerodynamics part
More
1.
in depth in the flight controls chapter.
And we got 2 more parts to go over here. Before I jump into part 2, any questions about the first bit of information? All right, let's jump into part 2.
Tutorial 4, Aerodynamics of Flight. Axes of an aircraft will be covered more in depth in the flight controls chapter. However, it is important to know the 3 axes that an airplane can move on. The first is pitch. The pitch, or lateral axis, is the point that a plane will pitch its nose up or down on. The roll, or longitudinal axis of an aircraft, is the point where the airplane will roll to the left or right. And the yaw, or vertical axis, is the axis that the plane will yaw on or move its nose left and right. It is also important to note that each of these lines runs through the airplane's center of gravity. Each aircraft responds to control inputs differently, and therefore handles differently. For example, a smaller aircraft might respond rapidly to control inputs, while a large transport aircraft may feel sluggish and slow to respond to inputs. These features can be designed into an aircraft to facilitate the particular purpose of the aircraft by considering certain stability and maneuvering requirements. There are 2 types of stability: static and dynamic. Static stability refers to the initial tendency or direction of movement back to equilibrium. In aviation, it refers to the aircraft's initial response when disturbed from a given angle of attack, slip, or bank. Positive static stability is the initial tendency of the aircraft to return to the original state of equilibrium after being disturbed. Neutral static stability is the initial tendency of the aircraft to remain in a new condition after its equilibrium has been disturbed. Negative static stability is the initial tendency of the aircraft to continue away from the original state of equilibrium after being disturbed. Dynamics.
Real quickly here. Again, she doesn't really touch much upon this in greater detail, but to give you an example of the three different types of stability. Positive stability is what you're mostly going to see in the civilian world. It's also what's most aircraft trainers, like the Cessnas and the Pipers, things like that. The reason being, it's a very, very good safety feature, because if you were to put it in a different angle and it causes the aircraft to stall or whatever, it'll eventually correct itself on its own and go back to its original position. Good thing with aircrafts like that is, for instance, if you put the aircraft into a spin, whether it's during training or whatever, and the aircraft starts to do this downward spiral, most aircraft, like the Pipers and the Skyhawks that have positive stability, after maybe a couple of spins, even though it'll feel like forever and you'll probably be terrified to death, it'll eventually correct itself and fly itself out as long as you let go of the controls and do nothing. Now, of course, there'll be maneuvers that'll teach you how to get yourself out of a spin in later training as far as a pilot goes, but as far as basic entry-level stuff goes, if you leave it alone, it'll fix itself. Now, neutral stability is more what you see with like stunt planes, like at air shows, where it can go like this and this and this, and does all these crazy maneuvers, and it just stays there. That's what a neutral stability is. Once it points its nose where it wants to go, that's where it goes. Negative stability you'll see mostly in military aircraft, like fighter planes. How negative stability works, I don't know. Most of the time we just call it PFM, pure freaking magic. That's how the military flies, on pure magic. You know, if they basically just put it wherever and it'll still do its own thing and go somewhere else. It requires a lot of coordination to keep the aircraft constantly where you need to go. But the negative stability does give a lot more maneuverability and overall control of the aircraft than these other two. And that's why the military is able to use negative stability to do a lot of crazy, crazy maneuvers, and even at high G's, high gravity pull. Any questions about the stabilities? No? All right.
Angle of attack, slip, or bank. Referred after being disturbed. Dynamic stability refers to the aircraft response over time when disturbed from a given angle of attack, slip, or bank. This type of stability also has three subtypes: positive dynamic stability, neutral dynamic stability, and negative dynamic stability. These act in the same way as the static subtypes, but these subtypes explain the same relation over time as shown on the above graph. Stability in an aircraft affects two areas significantly: movement and controllability. In designing an aircraft, a great deal of effort is spent in developing the desired degree of stability around all three axes, but longitudinal stability about the lateral axis is considered to be the most affected by certain variables in various flight conditions. Longitudinal stability is the quality that makes an aircraft stable about its lateral axis. An aircraft with an unstable longitudinal axis will have a tendency to dive or climb and can become unsafe to fly. Static longitudinal stability or instability in an aircraft is dependent upon three factors: location of the wing with respect to the center of gravity, location of the horizontal tail surfaces with respect to the center of gravity, and the area or size of the tail surfaces. The above picture shows these forces balanced in flight. The center of lift in most asymmetrical airfoils has a tendency to change its fore and aft positions with a change in the angle of attack. The change in lift tends to move forward with an increase in angle of attack, and to move aft with a decrease in angle of attack. This means that when the angle of attack of an airfoil is increased, the center of lift, by moving forward, tends to lift the leading edge of the wing still more. This tendency gives the wing an inherent quality of instability. Most aircraft are designed with a nose heavy or a center of gravity that is in front of the center of lift. Even when the horizontal stabilizer is level during flight, downwash from the wings pushes the horizontal stabilizer down. Generally, the manufacturer of the aircraft will give the horizontal stabilizer an angle that will provide the most stability during flight at a given speed and power setting, as shown above. For a nose-heavy plane, when the airspeed is slow and there is less downwash on the tail, the nose will pitch over more aggressively. Thrust can also affect the longitudinal stability of an aircraft. Reduced power causes less downwash and causes the nose of a nose-heavy airplane to naturally pitch down, which is a desirable characteristic in an aircraft in order to make stall recovery easier.
Now, a couple of things that she didn't really go into greater detail that is a bit important here. Has the angle of attack ever been discussed with you guys before? Do you know what the angle of attack necessarily is? Yes?
Yes, sir. Aware of.
You're aware of the angle of attack? All right, for those of you who don't know, basically, this is a really bad drawing, so bear with me here. I mostly just do stick figures. The angle of attack is basically the center line of the wing, which is known as the chord line, is in relationship to the relative wind. And that's known as the angle of attack. Can you guys see over here? Let's turn on the light. Shield your eyes here for a second. I'm pretty sure it's going to blind you guys. So basically where the relative wind is in relationship to the chord line of the wing is known as the angle of attack. So if you want to climb, you change the angle of attack. So the relative wind is here, but this is a very drastic angle of attack. But the relative wind is different from the angle of attack. It's a greater angle here, and therefore will cause the aircraft to climb. Same thing if you do it the opposite way, obviously. Do it that way, you have the wind over here, it's going to cause it to go down. You ever stick your hand outside the car while it's driving? You know when you angle it down, your hand forces it down, or you do it, or you angle it up, it forces it back up? That's basically how this works. It's your hand, center line here is the chord line, and then basically how you change it to the relative wind when you're in the car changes the angle of attack. Any questions about that? Okay. Now there's still some more I'm going to go over here, but we don't need the lights on. The other thing that she didn't really go over was how the center of gravity can really affect the balance and stability of the aircraft. And most of the time, the center of gravity is controlled by you, the pilot, and what you allow in your aircraft. So you got your pilot's license, and you decide you're going to take a couple of your buddies and fly to the beach. So you load it up with fuel, your friends, some food, some drinks, and you go to take off. But you didn't do proper weight and balance. You put some of your heavier friends in the back seat, and of course all your supplies that you bring with you in the back as well. That's going to make the center of gravity farther back behind the aircraft, which can be extremely dangerous if you stall the aircraft. In fact, an aft center of gravity is the most dangerous thing you can have because it causes you to have less controllability of the tail section, and sometimes it can be so heavy it can cause the aircraft to just constantly rotate up and put it into what's known as a tail stall. And because it just stays like this, there's no way you can force that nose down to recover. It's just going to stay there because it's just so heavy back there, and boom, causes it to crash. Kind of like, did you guys see the video about the military C-130 that took off and just kind of tanked to take off? No? You have?
Yes, sir.
Okay. For those of you who haven't seen it, it was pretty horrible. Happened about, I want to say maybe 8 months ago or so, give or take. It was a C-130 taking out of Afghanistan, and they had it loaded with I want to say about 5 or 6 Humvees, which are military trucks. And during takeoff, something happened and all the straps that were holding the Humvees down snapped, and they started to just kind of pile up behind each other at the back of the tail. So while it's climbing, it just has this ridiculously high angle of attack. It can't hold it because it's already at a low speed while it's trying to climb, and it just goes boom, full fuel and everything, just big, big, nasty fireball. You know, obviously all on board died. I think it was mostly just the crew. I can't remember if there were any passengers, you know, soldiers going home. I think it was mostly just the crew, which is like maybe 8 people or something like that. But still, the aft center of gravity is probably the most dangerous thing you can have. Yes?
Yeah, Airman First Class International. Sir, I think you mean by the 747 they crashed out of Afghanistan?
No, 747s usually aren't cargo carriers. Not like that anyways. The military usually uses C-130s.
I've seen a video that on that's on the 747 taking out the ground and crashing.
It may have happened, but the one I'm talking about, I'm pretty sure is either a C-130 or I forget the designator, but it's called a Galaxy. And usually military use that as their cargo planes, either a C-130 or the Galaxy. I think it's a C-5 or something like that. Yeah, sure.
It's a C5.
C5, okay. I figured you'd bump in there, you have a military buff. It was either one of those 2 aircraft, and it was loaded, like I said, with about 5 or 6 Humvees. 747, like you pointed out, usually the military doesn't use. I think the only 747 the military really uses is Air Force One, when the president's on board. Most of the time they usually use their own military transports, like the C-130. But either way, both, you know, the C-130, I'm pretty sure it was a C-130 because it had props on it. C-130s, you have 4 propeller engines, and the Galaxy usually has a jet engine, but whatever, that doesn't matter, it's kind of null and void. Anyway, the other type of center of gravity issue that's not as bad, but still not good, is a forward center of gravity, where it's forward past the normal center of gravity is supposed to be. Usually, that doesn't happen too much in most aircraft, because most of the time, center of gravity is usually right where the engines are. Like especially on the Cessna, like this guy here. You get the side cut that we had earlier. That was a better picture. Like here's the Skyhawk right here, which is typical trainer. This is what I fly in most of the time. You see where the center of gravity is already. It's right there at the firewall for the engine. So it's really hard for something like a trainer to get a forward center of gravity where it's just so heavy it's just going to stay like this, on which is, you know, obviously hard to take off on, because you can't, again, pull the tail down enough to get enough lift to pull it up. Most of the time, a forward center of gravity can be dangerous, usually at slow speeds. Mostly, the bigger risk is at landing, because you're going at a slower speed, but you're trying to keep the nose up so you can flare. Well, if you've got a forward center of gravity, it's going to go down like this, and you're going to plow into the ground. Also not a good thing. But out of the two, the most dangerous is usually aft center of gravity, because you lose complete control of that, and you're just going to flap smack right into the ground like a pancake. I think that just about covers it. I think she'll go into more detail about weight and balance in a bit more here, but just to cover it anyways. Another thing you don't want to do is weigh too much. Center of gravity is dangerous, but having too much weight on the aircraft is also a bad thing, mostly for the structural stability of the aircraft, especially at bad weather or landing purposes. The instructor for the class here that I take, Brad, he told us a story of this one, rich guy, had a plane kind of like this, twin engine, about 6 people can fit on it. Same thing, packed all of his, a couple of his rich buddies in, and, wanted to fly them to some island nearby, like Nantucket or something like that. And he overloaded the aircraft. He had a full tank of fuel, which wasn't necessary for the trip they were taking, and also way too much luggage and people. And instead of either losing some of the luggage, which God forbid someone doesn't have their designer clothing with them, or dumping out some of the fuel, which could be expensive, that's another bad thing. It's not a good thing, it's expensive. they decided to just take off with weight. They barely made it off the ground. Like, they used the entire runway. And you're talking like a 5,000-foot runway for a small little plane. Usually you only need maybe 2,000 or so, give or take. So they're flying, and it only is maybe about half an hour to an hour flight to where they're getting to. So they might have only burned maybe, I want to say maybe 10 gallons of fuel, and that sucker can hold a lot of fuel, and the gas is pretty heavy. So they're coming down on final, and they're still way outside of the weight limit. Their center of gravity is okay, I believe, but their weight was still overweight. And as they touched down, landing gear collapsed. It just snapped out from under it, and they belly flopped on the ground. Completely totaled the plane. So center of gravity is very important. Weight is almost just as important, just for the structural stability of the aircraft. Another dangerous thing about overweight while flying is the wings. If you're flying and you're overweight, the wings have some flexibility. It's designed that way to help catch the air and also, keep you aloft. If it was hard, if it was just a solid structure, it would most likely snap. So it needs to have that flexibility. Well, if you're flying and you get into some type of turbulence or any type of bumpiness, and you're overweight and it overstresses the aircraft and it beyond its safety measures, it can easily just snap the wings right off too, which is also a very dangerous thing by being overweight. So usually, if you're within the proper weight limits and also within the safe speed limits as well, and you hit turbulence, usually you're okay. But if you're overweight, it can still cause snapping. Or if you decide to suddenly yank it up or yank it down, or even just put it into a steep turn or something like that, and just suddenly add extra G's onto the wing stress of the aircraft, and you're overweight, again, you can cause the wings to rip off. So center of gravity, very, very important. And of course, if you go to flight school and take the lessons, they'll teach you about it in more detail, how to make sure it's all balanced and everything like that. But center of gravity is very important. Weight is also important as well. Any questions? All right, cool. Let's continue.
Of instability. Most aircraft are designed with a nose heavy or a center of gravity that is in the front of the center of lift, slow longitudinal stability. Stability about the aircraft's longitudinal axis, which extends from the nose of the aircraft to its tail, is called lateral stability. There are four main design factors that make an aircraft laterally stable: dihedral, sweep back, keel effect, and weight distribution. A dihedral design is when the wings are connected to the fuselage a few degrees higher than from being perpendicular. Therefore, when the aircraft is viewed straight on, the wings point slightly upward like a V. The angle of attack stays high if one wing is lowered and will attempt to lift back to its stable position. If the other wing is lowered in the process, it will then be lowered and raise up until the oscillations subside. In addition to a dihedral design, aircraft may also have wings that are swept back. This design allows the lower wing's leading edge to hit perpendicular to the relative wind. This causes greater lifting effect, and the wing restores to its original position. An aircraft always has the tendency to turn the longitudinal axis of the aircraft into the relative wind. This weather vane tendency is similar to the keel of a ship and exerts a steadying influence on the aircraft laterally about the longitudinal axis. When the wing dips, the weight of the lower half of the plane acts as a pendulum to steady the aircraft. This effect is called the keel effect, and its effectiveness can be changed by weight distribution to make more of the aircraft under the center of gravity.
Now, real quickly on that stability there. What is the most likely thing to cause an aircraft to have instability laterally? Because you got the center of gravity here. So what would cause the instability here on the wings? Yes?
Cadet Master Sergeant Schreiner, too much fuel on one side and not the other, sir.
Correct. Now, that is usually not a problem with the trainers, especially with the Cessna Skyhawk, because most of the time you have a fuel selector valve, and Skyhawks can have an option of setting it on both, so it pulls equally on both sides of the tank. That's more of an issue with small planes like the Piper, where you have to constantly switch from one tank to the other, usually every 15 minutes of flight. Now, of course, that can still apply to bigger aircraft, like even this guy right here, like Barons or King Airs. They still have an issue, and also on top of the fuel distribution, with bigger aircraft like the Baron and the King Air, you also have luggage, because you have little luggage compartments here on the wings. So if you add extra luggage here, that can also cause some instability, especially if it's not balanced out on both sides. Most of the time, pilots are pretty well aware of the fuel after hours of training, because most of the time, that's part of the training, is learning how to switch the fuel tanks. You'll start to notice, in flight, if you're starting to get a distribution, because you'll kind of get that listing thing. And if you just check your fuel gauge and you see, oh wow, I had to switch over to this one for a while, you switch to the other tank, it'll eventually just equal itself out, because, as it was stated earlier, most trainer aircraft or small aircraft like this, or any kind of civilian ones, are usually positively stable. So once you correct the imbalance, it automatically fixes itself and goes back to stable flight. Any questions? All right.
Stability about the aircraft's vertical axis, the sideways moment, is called yawing, or directional stability. Yawing, or directional stability, is the most easily achieved stability in aircraft design because the vertical fin and the fuselage aft of the center of gravity are the main contributing parts that cause the aircraft to weather vane or point its nose into the wind. If the area of the fuselage aft of the center of gravity is larger than in front of the center of gravity, the aircraft will be vertically stable. Also, to add to the stability, a vertical fin is added much like the feather on an arrow. The fin, being placed on the tail, helps keep the wind from yawing the aircraft to the left or right. Free directional oscillations, or Dutch roll, is the tendency of the aircraft to yaw and roll in a figure-8 formation. However, most aircraft are built with spiral instability instead. This instability causes the plane to yaw in one direction, and if not corrected, the aircraft will enter a deep spiral dive. However, this tendency is usually easily controlled by the pilot.
A little story about the Dutch roll. If you ever get a chance to go flying with another friend who's still learning certain things in a bigger plane, and you're in the back as a passenger, don't. I had misfortune of, it was still fun, don't get me wrong, because it was cool to go in a bigger aircraft and learn how to fly, but I was a passenger in the trainer we have over Queen City. It's a Piper Lance. It's about like this, about a 6-seater, except instead of a twin engine, it's a single engine on the nose, just like a Cessna or a regular Piper. And the guy was going through commercial training with the instructor, and they were learning some other maneuvers that commercial pilots have to go through. The problem was he had some difficulty controlling the yawing factor. He couldn't really kind of just keep his foot on the pedal just right to keep that ball centered. So it started to do what they say, which is a Dutch roll. This is a Dutch roll. This is basically what it is. And if you don't correct it, it can become dangerous and become lethal. Thankfully, he corrected it, so pretty much all that happened was I got really nauseous. This constant, just looking at this, it's basically like a boat rocking up and down, up and down. It got me really sick. It was not fun because I'm in the back. Up in the front, you're in control. You know what you're doing, so you can usually predict how the aircraft is going to go at that point in time. When you're a passenger, you can't see what's going on. You're basically at the mercy of the pilot. So you're getting this kind of constant up and down, left and right. The Dutch roll was not fun. It was probably the least fun I had in that aircraft in flying, period. It probably took me at least 15 minutes after he finally corrected it for me to feel all right. But thankfully, it didn't get any worse than that. And then of course, they started doing other maneuvers like the chandelle, and that got crazy. But yeah, a Dutch roll, while dangerous, if fixed before it gets dangerous, mostly it's just unpleasant for passengers. So, just a little fun story.
An aircraft is not turned like a car or a boat. To turn, the aircraft must be banked. When the aircraft is banked, the lift acting does not act straight up and down. In a turn, the lift component is broken up into a vertical and horizontal component. The horizontal component is the force that is involved with turning the plane to either side. If the lift and weight continue to act straight up and down in a bank, the plane would remain pointed in the same direction. The rudder is used to correct any deviation between the straight track of the nose and tail of the aircraft. A good turn is one in which the nose and tail of the aircraft track along the same path. If no rudder is used in a turn, the nose of the aircraft yaws to the outside of the turn. The rudder is used to bring the nose back in line with the relative wind. The important thing to consider is that the horizontal lift component, not the rudder, is used to turn the plane. During a turn, the aircraft loses some of its vertical lift, which requires back pressure on the elevator to maintain a consistent angle of attack. Also during a turn, the increased drag causes the airplane to lose airspeed. If a constant speed, constant rate turn is required, then additional power may be needed. An aircraft is balanced whether it is in straight and level flight or in a climb. However, to transition from straight and level to a climb, there must be back elevator pressure applied. When this happens, the wings have an increased angle of attack and momentarily generate more lift. If no power was added for the climb, the airspeed would gradually diminish because the thrust required for a climb is greater than the thrust required for level flight. An aircraft is able to climb at a certain airspeed only because of excess thrust. When this thrust is gone, the aircraft will no longer be able to climb and will start to lose airspeed. This same principle is applicable to descents. During a descent, elevator pressure is applied forward, which causes the wings to momentarily have less lift. This causes the nose to drop, and the airplane will start to descend. This time, the power must be reduced to maintain a constant airspeed. When an aircraft rapidly loses lift on its wings, a stall occurs because the critical angle of attack for the airfoil has been reached. Stalls are one of the most misunderstood areas of aerodynamics because pilots often believe an airfoil stops producing lift when it stalls. In a stall, the wing does not totally stop producing lift. Rather, it cannot generate adequate lift to sustain level flight. Most aircraft are designed to stall from the wing root out to the wing tip. This provides the ailerons to have some authority during a stall. The stalling speed of a particular aircraft is not a fixed value for all flight situations. But a given aircraft always stalls at the same angle of attack regardless of airspeed, weight, load factor, or density altitude. A stall can happen at low or high speeds, and during turns, not just when the aircraft is flying slowly. In the picture above, the pilot is traveling at 100 knots, but pulls back on the elevator sharply. The result is that because gravity and centrifugal force prevent the aircraft from immediately changing directions, so the angle of attack is increased from low to very high, and the aircraft gets stalled. When centrifugal forces are added, such as in a turn, the stall speed increases. Most training aircraft are built with the center of gravity in front of the center of lift. This means that during a stall, the aircraft will rotate about its center of gravity and nose down. This condition is better than having the center of gravity behind the center of lift, because if the nose cannot pitch down during a stall, the aircraft will remain in a stalled state until it contacts the ground.
Until it contacts the ground. Again, that's the danger behind the aft center of gravity. It will stay back there until you contact with the ground. So that's why center of gravity is very, very important. And also, she's going into the load factor there as well. Again, that goes back to how heavy you are. If you're heavier than you should be, obviously you can stall at a higher speed. than if you're lighter. The lighter you are, the slower you can go before you stall. And also there's other factors that they'll get into, like flaps and all that kind of stuff too, that can help you generate lift at slower speeds. But basically, the heavier you are, the faster you stall. And of course, center of gravity also plays a factor into stall recovery, or how quickly you can stall.
Ice is allowed to accumulate on the aircraft during flight. The weight of the aircraft is increased, while the ability to generate lift is decreased. As little as 0.8 millimeters of ice on the upper wing surface increases drag and reduces aircraft lift by 25%. Pilots can encounter icing in any season, anywhere in the country, at altitudes of up to 18,000 feet and sometimes higher. The aircraft propeller consists of 2 or more blades and a central hub to which the blades are attached. Each blade of an aircraft propeller is essentially a rotating wing. As a result of their construction, the propeller blades are like airfoils and produce forces that create the thrust to pull or push the aircraft through the air. A cross-section of the blade shows that the top surface has a camber much like the top of the wing, and the bottom is flat, much like the bottom of a wing. The chord line in a propeller is the line drawn from the leading edge to the trailing edge. On a propeller, the thicker end is the leading edge. As shown above, each section of a propeller blade moves downward and forward. The angle that the propeller strikes the relative wind is its angle of attack, which produces thrust. Also, this blade's camber acts just like a wing to create forward lift. The pitch or blade angle says how much of a bite the propeller has or how much air it handles in one rotation. On most smaller aircraft, the pitch or blade angle is set and cannot be changed. But in larger aircraft, the pilot may change this to adjust the load on the propeller and to control engine RPM. These propeller systems are called constant speed propellers. Propeller efficiency can range anywhere from 50 to 87% depending on how much it slips. Propeller slip is the difference between the geometric pitch of the propeller and its effective pitch. The difference is geometric pitch refers to the theoretical distance a blade should travel through the air, and the effective pitch is the amount the blade actually travels. If the effective pitch is in a shorter amount of time than the geometric pitch, the propeller travels through the air too quickly, and that is referred to as a slip. The reason a propeller is twisted is to ensure that when the blade is spinning, the angle of attack of the blade to the air stays the same. If the blade were not twisted, for example, the part of the blade near the hub would be traveling slower than the part of the blade near the tip. This causes the part of the blade near the hub to potentially have a negative angle of attack, and the part near the tip to have a high angle of attack and be stalled during cruise. Therefore, to maximize the efficiency of the blade is twisted. To the pilot, torque, or the left turning tendency of the airplane, is made up of 4 elements which cause or produce a twisting or rotating motion around at least one of the airplane's 3 axes. These 4 elements are torque reaction from engine and propeller, corkscrewing effect of the slipstream, gyroscopic action of the propeller, and asymmetrical loading of the propeller, or P-factor. Torque reaction causes the aircraft to roll because the engine components are moving in one direction. So, according to Newton's third law of physics, on the airplane above, there must be an equal and opposite reaction. Most newer aircraft are built with their engines offset to counteract this tendency. When the airplane is on the ground, this roll tendency is translated to the vertical axis and causes yaw. During takeoff, this yaw tendency is canceled by the pilot's use of rudder. Because of the high-speed rotation of the blade, the slipstream ends up being a corkscrew, which yaws the aircraft about its vertical axis. The more compact the spiral, the more predominant the force. However, as speed increases, the corkscrew elongates and becomes less effective. When airborne, this effect also causes the aircraft to roll on its longitudinal axis. The rolling moment caused by the corkscrew flow of the slipstream is to the west, while the rolling moment caused by the torque reaction is to the left. These forces would seem to cancel each other out, but they vary greatly, and it is the pilot's responsibility to control each tendency, regardless of which is more prominent. To understand gyroscopic action, you must first understand how gyroscopes respond to forces. The picture on the top shows a force being applied to a gyroscope. From the force acting upwards on the gyroscope, it should be noted that the response is yaw instead of the expected pitching motion. This is because when a gyroscope is spinning, the resultant force always takes place 90 degrees in the direction the gyroscope is spinning. In an aircraft, we can simulate that same force by pitching the nose up and down. The applied force is from the tail of the aircraft, and the resulting force takes effect 90 degrees in the direction the propeller is spinning, in this case counterclockwise from the pilot's view, and therefore the plane would yaw to the right. The pilot must control this motion with proper use of the elevator and the rudder.
Now, real quickly here, this usually happens strongest at takeoff. Now, because it turns to the right, usually you have to step on which rudder pedal to get it back on course.
Master Sergeant Schreiner, the officer.
Close. You actually step on the right. Because it yaws to the right, the ball is going to go to the right, so you have to step on the ball. And that, you guys know what the ball is, right? Okay. So you have to step on the ball. So by stepping on the ball, you get it centered again, and therefore it prevents it from yawing to the right. So, it's weird, I know, but you always give it right rudder when you're taking off. Otherwise, it will veer away. If you still give it the other way, you actually just exacerbate the turn.
When an aircraft is flying at a high angle of attack, the blade of the propeller moving downward has a bigger bite than the blade moving upward. This causes the center of thrust to be moved to the right side of the prop disc area, which causes a yawing movement toward the left. The reason is that the blade moving downward has a greater speed through the air because it's moving into the wind, while the blade moving up travels with the wind. Because the propeller is an airfoil, the faster the blade moves through the air, the more lift it produces. Therefore, the faster moving blade causes an unbalanced forward thrust, called P factor, or the asymmetrical loading of the propeller. Please help us spread the word about pilot training system, and we look forward.
All